Boys, today we are looking at the hyperbola. It's a different type of function, and linked with that is the idea of inverse variation. So when we looked at linear functions, we talked about direct variation. Hyperbola is an example of inverse variation. So, inverse variation. When one variable varies inversely with another, one is a constant multiple of the reciprocal of the other. This means that as one variable increases, the other decreases, and vice versa. So, for example, speed, like to travel a particular distance, it's like a fixed distance, speed and time. Speed and time are inversely proportional. When traveling a fixed distance. Okay, and so the formula for inverse variation is this one here. Y equals k over x, so it's the form of a hyperbola in structure, where k is the constant of variation. So let's look at an example of inverse variation. Building a shed in 12 hours requires 3 builders. If the number of builders n is in inverse variation to the amount of time, t hours, find the equation of n in terms of t. So n would be equal to k over t. Where k is the constant. Now to find k, what we'd need to do is substitute in what we already know. So we already know that 12 hours requires 3 builders. So if we sub those in, so that is where n is 3. And we don't know k yet, and we know that t is 12. So multiplying by 12 on both sides, we get k equals 36. And so therefore our equation relating n and t is n equals 36 over t. Now we've got the equation, we can find out any amount. So find the number of builders it would take to build the shed in 9 hours. So to do it in 9 hours, we just need to go n equals 36, and then substitute in, instead of t, put 9, so that will give us 4 hours. 4 builders, sorry. Part C, find how long it would take 2 builders to build the shed. So this time we're putting 2 into our equation. So 2 equals 36 over t. Solving that, if we multiply by t on both sides, we get 2t equals 36. And dividing by 2 on both sides, we get t equals 18. Okay, so that's the idea of inverse variation in sort of a practical context. Let's look at like what this hyperbola actually looks like visually, and just go into a little bit more detail about this function. But wait, there's more. Let's do d first. Let's draw this function. So we're going to do for t equals 1 up to 9 here, and we're just going to graph it. So alrighty, so if t is 1, put 1 into the equation, we get 36, and then each time it's going to drop off. Okay, so if we put 2 in, we get 18. We get 3 in, we get 12. 4, 9. This is where it starts to get not as nice. So 36 divided by 5, 7.2. 36 divided by 6 is 6. 36 divided by 7, 5.1. 36 divided by 8 is 4.5. And then divided by 9 is of course 4. So then graphing that here, we're going to see that it decreases pretty steeply to begin with, and then sort of flattens out as it goes. So 1 at 36, 2, 18, 3, 12, 4, 9, 7.2. That one's a bit tricky to do. That's better. Okay, and so we can see then the slope down going from there. So if we just have a crack at drawing that. So it should just be a nice curve that heads up like that. So the sort of shape I was going for is that. Okay, so moving on to the next section. Okay, so with the hyperbola, we can see that there's the form that we talked about for the inverse variation. And so for the basic example there, y equals 1 over x. I'm not going to plot all these points. I'm just going to put some of the major features on it. So things to note, that this particular graph is going to go through 1, 1. And also negative 1, negative 1. And the shape that you get in the first quadrant is a bit like what we had before. So without plotting the points, it's going to get a shape like this, and then a mirror sort of image one down the bottom there. And so there is our basic hyperbola. y equals 1 over x. Okay, so just a little point here on continuity. So most functions have graphs that are smooth. Unbroken curves. They're called continuous functions. However, some functions are discontinuous or have discontinuities, meaning that their graphs have gaps or breaks. These are called discontinuous functions. The hyperbola is discontinuous because there is a gap in the graph and it has two separate paths. The graph of y equals 1 on x also does not touch the x or y axis, but it gets closer and closer to them. We call the x and y axis asymptotes, lines that the curve approaches but never touches. To find the shape of the graph close to the asymptotes, or as x approaches positive and negative infinity, we can check points nearby. Okay, find the domain and range of f of x equals 3 on x minus 3 and sketch the graph of the function. Okay, so something to note here would be that if we look at the structure of this guy, we do have a number greater than 1 at the top, and that's just going to affect the steepness of it. But the number down the bottom that is on the denominator, what that's going to do is that's going to shift the graph across. Because if you think about what x values or where in the domain it couldn't be at x equals 3, because if you put a 3 where the x is, you'd get 0 on the denominator, which we can't have. So for the domain, we're going to have negative infinity up to 3, and not including it. And we're also going to have from 3 okay, and so that's going to go up to positive infinity from there. So it just doesn't include 3 basically. And the range, it's not going to include 0 because it's not shifted up or down. So it will just be negative infinity up to 0, not including it. And 0 to infinity. So maybe jump on Desmos to have a look at what that will be like. And then try the last function there. Good luck.